Okay. Well, hello, everyone. Welcome back to the Topos Institute Colloquium. Today, we're very happy to have Mason Porter talking to us about topological data analysis of spatial systems. So the floor is yours, Mason.
Okay, thank you. So David, thank you very much for the invitation. I appreciate it. I will apologize in advance for some coughing. I had COVID a few weeks ago, and the cough has not gone away, and that's life. Then, as I go through, if there's some clarification questions, those are fine to bring up in the middle, just because I know those can be sticking points. But then more substantive questions, it's kind of better to ask at the end, I think. Okay, so my goal is to give an introduction to topological data analysis and what some collaborators of mine and I have been doing with them on spatial systems. Oops, let's advance the slide. Okay, so spatial systems are quite diverse, and they have a big influence on the structure and dynamics of systems that are in them. A reference that's useful to get started, and this is a Springer book, and many institutions can get it for free through Springer Link. So it's something that hopefully you can get access to. But it's a book called Spatial Networks by Mark Bartholomew. That's from a couple years ago. It's actually a bit of a sequel of different things that were. It's a sequel of a prior book, but the name got changed. Anyway, so this here is a granular system. It's quasi 2D, so it's really thin in 1D. And so the interesting stuff is taking place in the other two dimensions. And there's a couple of different sizes of particles. And then there's these bright spots with large forces. And you can see all sorts of different structures in them. And so that's one type. You could also have, say, disease spread on different regions of a country, or you could have, this is actually a rabbit warren. So rabbits are living, it's sort of like a 3D sort of road network. This is a fungal network. It's actually one fungus, which is basically a living network. This is a road network. This is in London. It's a center part of London. This is the metro network in London, sponsored by IKEA. This is a depiction of a brain network, and all these things are embedded in space. But even though we're in a low dimensional space as far as where the nodes and edges are, you've got a lot of diversity of different structures that show up, right? So just because we're in low dimensions, we're still having diversity of structures. One might look at these things topologically. And so I like showing this picture because depending on your view, it's either a dream or a nightmare. That this is the border between Belgium and the Netherlands at a certain point. And everything that's sort of gold is in Belgium, and everything that's sort of beige is the Netherlands. And you can see that this is not some simple border where you just go from one country to another. And imagine if I were starting here on this sort of road, and I'm in Netherlands, and then I'm in Belgium, and then very briefly, if I'm on the right side of the street crossing the Netherlands, if I'm on the left side of the street, I don't get back into Belgium, cross over through the Netherlands. So it's rather complicated, this particular border. So topologist dream or nightmare, depending on your view. And this is a complicated example, but it's one that actually shows up as relevant in real systems. And the reason is if you're using spatial data and you're using these what are called shape files, and you have things at zip code levels, if you look at different zip codes in different cities, like in New York, for instance, you actually do have some versions of these things, and you then have to deal with them if you're trying to do something topological on top of those structures. So even though this is sort of a complicated example, it's reflective of things one does actually have to deal with if working with data. So one of the things that we did, still in the intro part, trying to say quantify political islands. So this notion of trying to find, say, red voters in a sea of blue. So maybe the red voters are this blob in the center, surrounded by blue, like over here or over here. Or you might find light blue voters in a sea of dark blue, right? So somehow there's non-trivial topology and kind of constructing it that way. And we can look at, we're good at looking at these pictures and identifying it, but can we do that algorithmically? A fun example, another one that will show up, I guess, if I have time, towards the end, spiders spinning webs under the influence of various drugs. This is actually from empirical data. So this is caffeine. Cheers. And just what the webs look like, and maybe comparing the topological structures of them under different structures, right? So in the case of what we're actually doing is that we're taking the images and looking at this as image data and looking at what happens to the image data. An example of resource coverage, another, well, related to an example I'll get to later with maybe a less frivolous resource, but this particular paper, which is an interesting paper because it's an introduction to topological data analysis for people in the geographic information systems community. So that community has started looking at these things and even has their own sort of survey article now. This data set was one of the ones studied in this particular paper, the placement of pub locations in different cities in the UK. So resource coverage. Okay. If you want to learn more about these things, I've got 2 slides with references of various types, and there's other references that I can give. And there's references of different levels of mildness. I think given the audience, I didn't list as many of the more milder references this time, but I can provide them if they're of interest. One recent review article from Gunnar Carlson, he actually wrote this article for a physics audience. Although you can still tell when you read the paper, even if you didn't recognize Gunnar's name, that it's written by a mathematician, but he wrote this for a physics audience a couple of years ago. Then there's an article that I was involved in. The first author is Nina Otter and a couple other possibly familiar names on the paper. And this was for a particular type of topological data analysis known as persistent homology. And the point of this paper, in addition to having some review and survey type stuff, it's meant for people who have not done it before and they want to start getting into it. And so there's even software installation type discussions at some point in parts of the article. And so if you're interested in trying these ideas and you want to do them, this article is a good first place to go to help get you started. There's also various lecture notes and books of different levels of terseness. One set of lecture notes that's been made public and also has accompanying videos that have been made public is from Vidit Nanda from a course that he taught at Oxford. Officially, this is for their 4th year students, but you should view it as an introductory graduate course. So that's one sort of terse set of notes and videos to look at. And then there's a classical book by Edelsbrunner and Harrer, which I'm sure some of you have seen before. There are various versions available online. Another book that also has some various versions available online is more recent by Tamal Day and Yusu Wang. So those are also, they're more on the theoretical computer science side in terms of their perspective. But anyway, so those are some resources if you're interested. And I'm happy to share and post slides and so on, so you don't have to be frantically copying down URLs or anything. Okay, so going back to the sort of classics, so to back up a little bit, so there's the whole thing with donuts and coffee cups. You can actually buy these. This is a picture of a physical copy. So this is from Henry Segerman and Keenan Crane, and it's a video of a sort of morphing where you've got a coffee cup that is gradually morphing into a donut. And the thing that you see that is being preserved is this one hole over here. Right, so that's being preserved, and other things are just being kind of squished and just molded, and things that were allowed to change topologically, right? So we care about invariants like this number of holes and the number of connected components, of which there's one. Okay, so if we're looking at data, it might come in the form of a point cloud. It's not the only form it could come in, but it's a typical form. And maybe the point cloud looks like this. This is a certain Pokemon called Jigglypuff. But even if you don't recognize the character, you probably can see that there's a notion of ears here, and there's a notion of eyes, and a notion of feet, and maybe a notion of well, I was going to say hands, but more arms without hands. But we're humans are good at doing this, right? We are good at filling in these things, but then the point of TDA is how do you actually do this in a topologically meaningful way? Because if I just literally take a bunch of dots, well, I have a bunch of dots, right? So I want to somehow turn this into something that I can meaningfully look at in a topological way. Okay, so this is where the point cloud was taken from. So a bunch of us wrote an article for teens and preteens. This is one of the very mild references about what TDA is about. So that was a bit of a challenge that some of us did. And this particular example, which also brought up in various talks and used in other sources, comes from that paper. And so this is a full figure of it. So panel A is what I showed you a couple of slides ago. And what we imagine is that we take each of these dots, and instead of being literal points, we gradually increase the radius of these dots. And then what we saw with our intuition on our own starts looking better, right? So we start literally we have fewer components as we do this. And at first we gain some holes. I think we have not quite gained a hole here, but we've gained a hole over there. And then we've gained a couple more holes. And then the holes also gradually start filling in. So our notion of what this creature looks like also starts filling in a bit. And then eventually you have a blob, right? And so then the question is, well, what can I say topologically? So if I fix a radius, I can say something topologically about panel A. And if I fix a different radius, I can say topologically something about panel B. And so then the question is, how do these invariants, in this case, the number of connected components and the number of holes, change as a function of this parameter, which in this case is the radius of these dots. But in some other case, and this is actually something that's been an important consideration in the research papers, it doesn't have to be the radius of the dots. This parameter that you could control could be something else, and ideally will be related to whatever problem you're studying, and will be chosen in a way that's helpful for your problem that you're studying. Okay, this particular one is just summarizing what's on the prior slide, and it's saying the number of components, how they're changing. We use the word pieces in the article just to not use the word components for the kids, and how the number of holes are changing as well. And if you count the number of components, you're going to get Betty number 0. So now I'm just writing it down as H naught, I guess would be the fundamental group, but we're getting Betty number 0. And for 1D holes, we're getting Betty number 1. Okay, so we're counting topological invariance in doing this. Okay, so this kind of reiterates stuff that I mentioned verbally but had not yet written down. We want algorithmic methods to study data. Could be high dimensional. The examples I gave you were not high dimensional, and these spatial ones, in fact, are not high dimensional, but it can be. We want to do this in a quantitative way. So we want to do this algorithmically, because if we have many of these things, or if we want to compare the structure of many different ones, we can't rely on human ability to just do this. Humans are good at this, but we need something that scales up and is algorithmic. I showed you data from point clouds. It could come from networks. I was using some motivating examples from networks. It could come from images. The spider ones come from images. It could come from time series. That's not actually something that I personally have worked on as much, but other people have. And so we want to say, what is the shape in some topological sense of data? TDA often means persistent homology. It doesn't have to. It can mean other things as well, but persistent homology is the most common use. So again, mathematical formalism to study topological invariance of these data sets. The algorithms are fast. I probably should put fast in quotes. They're fast from the perspective of the topological things that have gotten implemented are the ones that you can do in a fast way. But if I put on my network science hat from other parts of my world, though they're not as fast as some of these standard network algorithms, but they do have more mathematical guarantees behind them, which is good. And then the notion of persistent structures, we want to say for many different radii of these dots, or for many different values of what other parameter that I'm using, we want structures typically that are persistent over a large set of these things, right? So we're trying to find structures that are there, even though there's also noise, right? Which things are actually real and which are noise. And the traditional thing is to say, well, if it exists for a large range of parameter values, then it's signal, and otherwise it's noise. Reality is a bit messier than that, but that's the sort of perspective that's taken. Okay, so give you a little bit, a couple ideas from algebraic topology that we need, and apologies for saying things that you know many of you know before, but it's still useful to do this. Okay, so I showed you this picture. So we want to describe the properties of an object that stay the same. We're allowed to stretch it or shrink it or bend it, but we're not allowed to glue things and we're not allowed to tear things. And so we seek topological invariance. Number of components. There's one here. Number of holes of different dimensions, so loops, cavities, and so on. So this has a one-dimensional hole over here. And we're going to consider today homological invariance, but there's some work on doing others, and advancing work doing other types of invariance is definitely a very relevant thing to do. Okay. All right, so we need the idea of a simplicial complex. Just to remind you, a K-simplex is a K-dimensional polytope that's going to be the convex hull of its K+1 vertices. We can have faces of different dimensions, so an M face is a subset of size m+1, and itself is an M-simplex. Okay, so we've got here a tetrahedron, and it's got triangular faces, but it also has edges, which are lower dimensional faces, and it also has points, which are even lower dimensional faces. A simplicial complex will be a set of simplices that satisfies a couple properties. Every face of this complex has to also be there. And then if two simplices have a non-empty intersection, then that has to be a face of both of the simplices. So I'm not showing that in a picture here, but I believe the next slide will have a picture that illustrates this second part. Yeah, so this is a picture from Wikipedia. And so, for example, this point over here is a face of both this and that. And you can also see that some triangles are filled in and others are not. What you're not allowed to have, and I don't have a picture of this, but if I have, say, two edges, I cannot have them partially overlap. They have to either only intersect in a point or the entire edges have to intersect. So I cannot have that. So I don't think I put this on any of the slides. Okay, so we want to use persistent homology, and so we're going to use ideas from algebraic topology, in particular from homology, to analyze data. Okay, so one thing I need from there is that I don't need just simplicial complexes. I actually want this notion of a nested set of simplicial complexes. This is called a filtered simplicial complex or a filtration, and it's going to be a sequence. And I have this sort of chain of containments in the sort of simplest version of this. There's some relaxations. And so you could think of S naught as like the set of points. And so each of these values here is basically choosing a different radius. So I choose a certain radius and I get a simplicial complex of these point cloud. And I choose a different radius and I get a simplicial complex, and so on. And so we filter by saying, well, what lens are we looking at the data at? And then we ask ourselves, if I'm measuring the connected components and holes of S naught and the connected components and holes of S1 or higher dimensional things as well, which of these objects exist across a large set of these simplicial complexes? So in other words, which of these things are persisting across scales? Again, think of the radius of the dots being increased gradually, and some of the structures appearing and disappearing. This is not supposed to be blank. That's okay. I apparently have this unintentionally left blank. I don't know what I was doing, and I hope it's not something that was important that I accidentally deleted, and I apologize if it was. Okay, so this is now going back to the intuition I was showing before, but now we have points. You can pretend this is a point cloud, even though there's a finite radius to them, just so we can see things visually. But now we put this blue radius around them, and we gradually increase them. And so when we do that, these three things are all pairwise adjacent. And so therefore, because they're all pairwise adjacent, I have this triangle here. And over here, these two are pairwise adjacent, so I have an edge. And then I can increase the radius, and now I've got four things that are pairwise adjacent, so I have a tetrahedron. Okay, and the hole that you get in the simplicial complex is this hole that's in the center over here. So the actual thing that we did in this picture, both in this picture and in the one that I showed you originally, is known as a Vietoris-Rips filtration. We fix the value of epsilon, and for each point we center a ball of radius epsilon There are various ways that people think about generalizing to make it heterogeneous, for instance, but this one was not. And whenever k plus one of these epsilon balls, and they overlap pairwise, so that's an approximation of what's known as a check complex, if you don't care about pairwise. But pairwise is something that makes things faster, so we're doing it. We create a k-simplex. That's why when I phrase this, I phrase it as a 3 being overlapping pairwise. I was purposeful in phrasing it that way. And then the resulting collection is a simplicial complex. And then we increment epsilon and we make it larger and we do it again. So that was the actual thing that we're doing. And there's some nice algorithmic guarantees if you're doing it that way. It's a specific construction, but it's a very common construction that people use in many situations. Things that you track, birth and death of features. So you say that a feature is born if this is the smallest I for which a feature exists. So say I suddenly see my radius epsilon is large enough so that I see a hole. The hole is then born at that value of epsilon. A feature dies if it's the largest value for which a feature exists. So at some point the hole disappears. And so the last one before it disappeared is when it's died. And there are various ways of tracking this in terms of summary statistics. There's two that I will show you, and so those are the only two I'll mention here, but there's actually quite a few others. Barcodes, which are so named because of visually what they remind some of us of, and then persistence diagrams. Persistence diagrams are nice because you can do things like defining a metric, although technically a pseudometric, on the space of persistence diagrams. So there's this notion of saying, I have two different structures, two different point clouds, say, and I do some sort of construction of simplicial complexes, and I produce persistence diagrams from two different ones, and I can say how far apart they are from each other in various ways. Okay, this is what a barcode looks like. So this is an example of a barcode. Epsilon here technically doesn't quite mean what it did before, but I'm just using it as a parameter. So this first part on top is saying, when are the number of components kind of combining and going down? And this one on the bottom is saying, well, when are holes being born and when do they die? And so this first part, because it's in the number of connected components, actually has all of them born at the same time, right? So we had a point in our point cloud, they're all born at the same time, and they die at different times. And for holes, it's a different situation, right? Because you can get born at various different things. And so some are born earlier than others. So the left endpoint is the birth of a feature. The right endpoint is a death. How long a feature exists is the death minus the birth. And visually, longer features are more persistent. You can plot the same data as persistence diagrams. This is one particular type of persistence diagram. I put birth on the horizontal axis. I put death on the vertical axis. So if I choose these axes, I can only have stuff in the upper half. So sometimes people will choose different axes. And so how far you are above this diagonal line, which is the birth equals death line, will tell you how long you live. And this top line this line at the way top, this pink thing over here is referring to a component that did not ever die. So I stopped tracking the death, and this component is still there. Doesn't mean that it won't die later. It just means I stopped tracking it, so I am viewing it as having lived forever. So infinity means I gave up or something. Although with connected components, you're always guaranteed to have one that lives at the end anyway, because of the nature of what it is. Okay, so I'm using pink circles to plot my connected components, and I'm using blue squares to plot the one-dimensional holes. And then the fact that these pink circles are all on the same vertical line is telling me that they were all born at 1. They were all born at the same time. Okay, so in principle then, being high above this diagonal line is supposed to mean that something has been there for a lot of values and that should be a feature. Okay, so let me show you a couple of studies in which we've used these ideas. So this is one with my former student, Michelle Fung, that appeared in Siam Review a few years ago now. And this is the one we were looking at kind of quantify political islands. And then one thing I want to talk about with this is how we were defining our filtered simplicial complex, how we were constructing it was one of the things that we needed to think about. So I showed you a specific construction, but in fact, we're going to want to do different ones for this data ultimately. Okay, so this picture comes from that particular paper, and so we're trying to say find this island algorithmically through some process like what I was describing. We have precinct level voting data. This is actually public data from an LA Times project. Precinct level voting data is much more finely grained than is often the case. Much more common is district level data. And so there's quite a lot to this data that we didn't look at. And so this is something that if people are interested in these ideas, it would be good. This is from the 2016 election. So the topological method should allow us to identify holes and also give us some idea of relating the presence of holes to a more global structure. So we want to find these political islands, and we're going to view these islands as holes in a manifold in which all precincts vote similarly. And actually, treating it as a manifold is slightly different than what we were doing in the other case. Okay, so one of the simplicial complexes that we defined, we call the adjacency simplicial complex, and we're trying to use network adjacency. And you can use either rook or queen adjacency in terms of different precincts, whether they're only hitting at a corner or whether they have to have some contiguous non-point boundary. If n+1 nodes, so nodes is a precinct, are pairwise adjacent, you define an n simplex if they're all pairwise adjacent. And then given appropriate node or edge data, you can construct a filtration. In our case, the node data is going to be based on what fraction of people voted for a given candidate, in this case, Clinton versus Trump. And so we're going to be determining this by, is the winning candidate, did they sort of win by enough in that precinct? So we're going to determine whether we keep that node or not. But you could also use, like if you're doing edge data, you could imagine like road traffic or something being data that one might use. So what we're tracking instead of the radius of a ball is the strength of preference for a candidate. And so we don't care about how large a precinct is. And this is actually why we were thinking of doing a construction in this way, but rather we care about how heavily a precinct favored a candidate. So that's the type of thing we're filtering by. We also use one other type of complex, which we call a level set VR complex. The reason we're using the term level set is because of what's known as a level set method, which is from computational PDEs. So the terminology has a little bit of overloading with other stuff that you've probably seen, but we're referring to this in a bit of a different way. Now we're using data in surface form, so we want to think of it as a manifold. And we're going to take a map of all precincts with similar voting patterns. So similar might mean they favored the same candidate. That's how we did it in the paper. But you could also demand similarity and how much they favored if you wanted to. And we're going to consider the outer contour as a zero level set of some three-dimensional object. And we're going to let it flow through the level set PDE, which is front propagation. So the partial derivative of phi with time just going through the gradient. So it's going to be, we imagine a front and we're moving this front in one dimension, and time is actually our filtration parameter. And we're going to then put this on a triangular grid and take the collection of filled grid cells to be two simplices, taking grid lines to be edges and taking points to be vertices. So this is a bit of an unusual choice of filtration, but we found out that it was useful for this particular application. So when I'm making comments about saying, okay, you have a certain application in mind, that informs mathematical choices that you make. So this is a comparison just visually. Okay, so technically we used what's known as the alpha complex, which is an approximation of the Vietoris-Rips complex. And we did that because we needed something that was faster in terms of how large the data was. So this particular barcode is the one that I showed you earlier, and that's why I made the comment that it wasn't technically Vietoris-Rips, but it's similar. The adjacency complex on the same data. So Tulare is a very Republican county, so it's in. I think it's near where Orange County is. So we use an adjacency one, we get a different structure. We use a level set one, we get a different structure. So depending on our filtration, we're getting totally different structures. And we're also therefore getting totally different barcodes. So this is distance-based, so it does care about the size of a precinct, but the data is really about different things. cares about the strength of preference. It's actually the relative strength of preference. So we're saying, okay, we demand 95% difference in strength of preference. Then we demand 82.5%. Then we demand 70%, and so on, right? So we're basically taking the less and less majority as we go through. And then the level set one, as we mentioned, is time moving. Okay, so visually, and this does turn out to be true, it appears that this third one is the one that's doing the best, because you can see that these islands are here, right? There's this blue within this red. There's this blue within this red, which is what our goal was. Okay, I didn't mean to quite press it then, but almost. So that was something we did there. Okay, so now so there's a lot more in that paper, but I want to just, again, I'm trying to survey examples. Here's another, this is more recent. It is in press in SIAM Review, and will be out officially, I think, August 8th or something. But you can find it on Archive, and it's a different set of students. So Abby Hickok, who is a former student now at Columbia University, Ben Jarman, who's a former student, Michael Johnson, who's a current student, and Jerry Luo, who just graduated, like literally just graduated. And so this is saying, let's look at access to where people are voting, as opposed to let's look at the outcome of the voting. So we're thinking of resources. So resources could be other things, could be the location of pubs, could be parks, could be DMV locations, could be whatever. And so a sort of comparison to the approaches that are, there's a whole literature on resource coverage. The sort of naive approach versus what we're trying to do. So typically what happens, and people say, well, let's take some threshold. And I'm phrasing it as a distance threshold. People often do this in terms of distance, although I'm going to argue that you should be more sophisticated than just doing distance. And they say, well, let's calculate how many people are within some distance, fixing the distance of a resource site, which could be where to go to vote or whatever. Or they might calculate which locations are within a given distance. And sometimes they'll consider more than one distance, but it's really being done in an ad hoc way. Okay, I mean, they could be more ad hoc, they could be less ad hoc about that if they wanted without doing pH, but they tend to not be. What we want to do is to look at all scales at once. So if you're doing distance, that would mean all distances D at once. But in fact, if you're thinking about voting and many other things, distance is not what you should actually be measuring, right? What you really care about is how long does it take, right? Because you might have a job and you might, we don't have voting as a national holiday. So we might have to take time off from the job and go somewhere to vote and then wait there, right? So you might have to wait in line. That also matters. And then go back. And so you have to sort of consider, so I think time is actually more relevant. Okay, that's, I guess more, I have that on a different slide. Okay, I guess I'll come back to that then. But we're looking at entire zones that are not covered rather than point-wise, and entire zones might correspond to certain areas of a city, and those areas of a city might have certain demographics, right? Because one of the things that we're concerned about with things like voting is there a systematic bias in who has practical access and who does not? Okay, so I got ahead of myself in terms of the time, measuring distance in terms of time. So you need something that's distance-like. It does not have to be a proper metric, but it has to be distance-like in some way. And we argue that for this application, time is appropriate. We consider travel time and waiting time. There are different modes of transportation. There is going to be the big issue of approximations based on what data we can get in practice. So that is a serious issue. And our limitations in this paper are quite long in terms of what we discuss partly as a result of data. But you can imagine that different situations in different zip codes of a city might have different fraction of people who have cars. And if you have a car versus if you have to take public transportation, that's a big deal. We were motivated in this project by Atlanta. If you remember what Stacey Abrams was saying with sort of her advocacy, that was so Atlanta was the first city that came to mind when we were doing this project, and then we wanted other cities to compare it to. We also need waiting times, right? Because you might go there and you might have to wait a while. You might have to wait a long while, especially if there are too few of these places to go vote. And so the way that we deal with that in this paper is to use weighted Viator Scripps filtration. And so what that will mean in practice is that I'm not going to start expanding the dots immediately. What I'm going to do is that at each location, I first have a waiting time. Say my waiting time is 5. I will only start expanding the dot at that location after 0.5. Okay, so there's a delay before the radius expands. And so the delay could be different for different dots. So there's a weighting in that. That's the sort of twist on the sort of standard Viator-Phipps filtration. Our waiting time estimates were at the level of congressional districts. This was from a paper from a few years ago. And this is less finely grained than is desirable. So we assume that all the voting locations within a district have the same waiting time. That is not likely to be true. That is not likely to be close to true. But this is what we have to do for the data that we have access to. Okay, so things that you can look at. One thing that's actually important that's different from here than from many things, the death values are what's important. Normally, you're looking at things like death value minus birth value, which tells you how long something lasts. But what the death value means is that this is how long it takes to vote. So a whole dying or feature dying means that that's how long I have to take to go to the place, wait, go back. And so even if something is born, even if a feature is born very late and doesn't exist for very long, it happens to be that when it dies for this particular application is what we care about, right? So we're computing something slightly different. And different cities, if we're measuring the death in minutes, have different ones. We chose 6 cities, and LA is technically LA County for various reasons. Atlanta was our initial motivation because of the controversies and the advocacy. And the other one we compared it to initially was New York City, because given the good subway system in New York City, our intuition was that New York City would be better. And then we started thinking of, well, let's consider other cities that are somehow different in flavor and that we expect to be different, right? So there's some notion of arbitrariness. The reason we only have 6 cities is we had to pay for this data, and we were willing to pay a few $100s, not a lot more. And so this restricted both the granularity of data within cities that we could get and the number of cities that we could do. Okay, so that's why there's 6 things as opposed to, what you really want to do is a comparison of a very large number. And then what's more arbitrariness involved is which are the ones that we chose. Okay, other than the motivation from Atlanta. And then you can see that, well, Atlanta doesn't appear to be doing that well, at least compared to these other cities. Some people in Atlanta are really having trouble. And then, so let's do another comparison that's a little bit more granular. And so this is Atlanta versus Chicago, looking at the 0D homology classes, which is connected components, and the 1D homology classes, which is the wholes. And the cost is time. So this is minutes on the horizontal axis and sort of count, so just frequency on the vertical axis. And the fact that Atlanta is shifted more towards the right is what's telling you is that there's more places in Atlanta that are taking longer than Chicago. So the fact that the distribution is shifted towards the right in comparison to Chicago. We pick Chicago here because, I mean, for one thing, it does actually do well compared to to most of the others. And we had intuition that it would, again, because of the public transportation that they have. Okay, spiders on drugs. And I'm conscious of time. I'm doing okay. And usually I have to cut off things. This is one example from a paper that actually has several different examples. And it's going to use the level set complex from this level set propagation. So this is also from a paper that Michelle Fung and I wrote a few years ago. And the paper is 2020, but it actually comes after the 2021 paper because the speed of physics publishing is faster than the speed of math publishing. But it uses a method that was developed in the other paper and just on a number of examples. And this is a fun one. Okay, so I showed you this slide before, but now I'm going to discuss it in a bit more detail. So the early work actually starts from pharmacologist Peter Witt, whose friend was being kept up late at night from spiders spinning webs at like 2 a.m. And I don't know what that sounds like or why that keeps people late at night. I mean, I'm in LA and we just have like helicopters all the time, and that keeps me up, right? But apparently spiders were keeping Peter Witt's friend up. So Peter's buddy asked Peter Witt, like, okay, well, you're a pharmacologist. Could you come up with some drugs to give these spiders so that they, I don't know, wouldn't spin their webs at 2 a.m? And so Peter Witt gave spiders drugs, and he has a whole career of half a century of different types of studies of giving spiders drugs. It's just quite astounding. I don't know. I mean, I'm a mathematician, and I look at these things and I'm like, okay, those are entire careers, spiders and drugs. There is a long tradition of giving various drugs to animals and seeing what happens from behavioral psychology and so on. Okay, so he did that. Now, 50 years later, almost, and there's just a 2-page NASA tech report. The Marshall Space Flight Center studied the webs of spiders that were exposed to various chemicals. So it's a 2-page report with like one table. So there's not that much stuff in it. But my understanding, although they don't actually say this, I think what they were trying to do was to find other animals other than, say, chimpanzees and so on. So animals that are sort of lower on certain scales, to see if they could actually do stuff with those. So they didn't say they were doing that, but that's my speculation. So anyway, they in both of these cases, they gave various chemicals to spiders and looked at the webs and computed some basic statistics of those webs, and concluded from that more toxic chemicals resulted in more deformed spider webs. So we have data from both of these, which is basically just like 7 different images. And so we digitized those images, and we just looked at the level set filtration and looked and computed persistence diagrams and just did that. So it's sort of a fun example that we have within this paper, that the paper is just a series of different examples. So this is the normal one, normal spider. This is caffeine. Caffeine's not looking very good. Again, cheers. We'll see what kind of spider webs I spin. Marijuana, which has a bunch of stuff, but it's not quite right. Speed. Chloral hydrate, which is what occurs in sleeping pills, or is one component of sleeping pills. That one's also running into trouble. And then we can compute that. So we have 7 different webs. The other ones I have here are peyote and LSD. So those I hadn't shown you earlier. So some of these images come from Peter Witt and some of them come from NASA. And then we have the persistence diagrams, both Betty 0 and Betty 1. And remember, I mentioned that we can compute distances between these persistence diagrams, so we could then do some sort of clustering. I think we used Wasserstein distance, but I would need to look up what we did. But you can use bottleneck or Wasserstein, and you compute a distance, and then you can then cluster it, in this case through average linkage clustering, and the drug-free spider is on its own, and speed and chloral hydrate and caffeine show up together, and marijuana, peyote, and LSD show up together. Now, normally, if you only have 7 things, you don't bother doing hierarchical clustering because you only have 7 things. But you can have more serious examples where people would do this. And so one example is the structure of city streets, which is another example in that paper. The reason that I'm showing the one with the spider webs is just because it's a nice, fun example, but you can do more serious ones as well. Okay, so then I'm going to give conclusions. I'm on time. I'm actually slightly early. This is amazing. Okay, so I gave you an introduction to topological data analysis, in particular through computation of persistent homology. And I also very briefly showed some stuff from a few different examples and with different constructions of this filtered simplicial complexes, right? So I do want to emphasize that you want to construct them in different ways. And they can give insights into structure and potentially also into dynamics. I was showing you structure more than I was showing you dynamics of spatial systems or spatial complex systems. There's an example where we've actually looked at spatial temporal data, but I did not show this to you. So this was a paper where we looked at vaccination rates for COVID and also COVID case rates itself, and looking how they how the latter changed through time. But that's in a different paper that I actually removed from the talk. Okay, so we looked at persistent homology of spatial, and you can do spatial temporal data. And we have low dimensional data. And one of the things that having low dimensional data does is that we can be a bit more systematic in the comparisons of what happens with different types of constructions. Basically, combinatorially, having the lower dimensional data means that less stuff can happen and the counting problem's easier, and therefore we can do things faster. So we were looking at 0-dimensional and 1-dimensional homology. You can go higher, but the computation times get more intense. Another thing that I want to emphasize in terms of the perspective that we were taking is that we incorporated information from applications into this. And so it's not just that we were using the software and kind of plugging away. And a lot of the application-oriented work that uses topological data analysis more or less just takes the software and uses stuff. The thing is, those use standard constructions, right? Like the Vietoris-Rips construction. And the Vietoris-Rips construction cares about distance, right? We have these balls that were increasing in radius. And some of these applications, distance, this physical distance is not actually what you care about. So the political islands is an example of that. The Spiderwebs is actually also an example of that. So other constructions, depending on your application, might be more appropriate. And so using information from the domain itself and from the problem you're studying in your mathematical construction is something that I like to emphasize, because there is this presence in the applied literature of just kind of using the software and using the standard methods and not thinking. So one has to be careful about that. Okay, I think that's all I wanted to say. So I can end the show and take questions.
Great. Thank you. Thanks, Mason. So for those who, if you have a question, just raise your hand on chat or just unmute yourself. Sorry, but to raise your hand, there's a button called reactions, and you press it. So any questions?
Yeah.
May I ask one? Yeah, go ahead, Kevin.
Hey, Mason, thanks a lot. It was really useful to kind of get an update from the finding a torus in a 9-dimensional space of images thing from 2009 that a lot of us have heard about, but not being involved in TA. Nice to see what's going on more recently. So I guess let me ask about the political one. You get this profusion of data out of this, right? Which is true, I think, usually. And
sorry, I had kind of two political ones. You mean this one, right?
Yes, the political island. Sorry, thanks. I want to ask about how you transfer this kind of work, or how you think about starting to be able to transfer into, say, policy recommendations. So you've got an enormous amount of data about there's holes, they exist at these time scales, and it's hugely non-deterministic how you get from that to if a policymaker wants to ask you a question, right?
Absolutely.
What's the path there?
Yeah, right. So yeah, let me address that. I would say, first of all, that we're extremely early on the path, right? So an analogy to think of is all the work with mathematical gerrymandering, where now they're very serious with the policy and so on, but look at how many years and how many people it took them to get there. And what it started out with is sort of applied geometry theorems, right? If you think so, we're still at the level of applied geometry theorems in terms of analogy with their thing. So one of the things that arises, the fact that we're using empirical data and looking at problems that people care about is good. I think the resource coverage one is more likely to have eventually a direct comparison to connection to policy. And I'm actually talking to people. And one of the things that we're doing there is that, I was mentioning how we have very serious data limitations. For a mathematician, the data limitations were okay, well, we just say in the paper what we do and what they are, and the sort of proof of concept still works. But it really is still a proof of concept. You go to the policymaker and you say, I sampled the data in this way, and you're done already, right? Because they can't do that. It's okay for a mathematician to do it. It is not okay for them to do it. So in fact, I would argue that for a lot of that, the next step is to get better data, because we spent a few $100. I can't spend a few $100,000. I do not have that. And so the hope is that the proof of concept interests people enough who are connected to those people who can help with the gathering of data And then the question is, when you have better data, do you get the same qualitative answer? So that's one step that we're taking now. And we were lucky with this other paper that it was covered by Wired. It was covered by Wired, which means that people who would not normally see it saw it, were interested. Many of them do come from mathematical backgrounds, or enough of them do come from mathematical backgrounds so that we can have conversations. And so what I've been doing is having conversations currently in the set of data. And I've actually been talking to some people from, I have to look up the name of their organizations, but the fact that we were looking at Atlanta helps, because Atlanta, there are people who care about Atlanta specifically. And so that's kind of a step there. And then the hope is that, so you talk to them and make sure you're not doing something stupid, right? So one of the people I talked to, for instance, were like, oh, you use cities, we think you should actually use counties instead. And again, for a mathematician, it doesn't matter, but for them, that difference in choice is a big deal, right? So you have these conversations and you get better data and you go gradually there. But yeah, there's really a big gap between where we are, which is very much proof of concept, and let's actually make the world better. I think you got muted.
I muted you, Kevin. Sorry, there was noises.
Oh yeah, there's traffic behind me. Yeah, thanks. Yeah, thanks. And like, for instance, you'll have to probably add in some geometry as well as the topology too, right? I was thinking in the resource coverage, if you've got a lot of first homology, but these are like small bubbles in the city, I guess maybe this is less policy relevant than if I have
that
a
depends
really
on
huge bubble.
that depends on who's in the bubble, right? Like my intuition, but this is now me as a human rather than me as a mathematician, is that those bubbles, even the small ones, might be particular underrepresented groups. Now, I don't know for sure. I can't assume that, and I have to separate me as a human from me as a mathematician. And we'd want to actually, like, verify it. You can't just pretend that what you think as a human before you do the analysis is necessarily true. But I would argue that a small bubble, depending on who it is, could still matter a lot. But yes, geometry is a relevant thing to do. There is also this maybe less common buzzword, but I think we're going to see it explode: geometric data analysis. So I mentioned my former student, Abby Hickok. Actually, her thesis has both topological and geometric data analysis, but the geometric data analysis was on other projects, and she's now pursuing that, especially in more detail, with Andrew Bloomberg. So we definitely, this is definitely on our radar, that geometry is also important.
Great.
Cool,
Thanks, Kevin. I had a question. It might be along the same line. So I don't know if this is interesting at all, but in terms of getting data, and I don't know if this works, but I think these large language models produce for any bit of text, they kind of know which words are likely to be associated with other words, like the word and the other word, those are associated strongly.
Right.
When you say he, it refers back to, it tries to guess which is the he and things like that. And I think maybe it offers actual numbers of guessed distances, which I imagined could be a huge source of data for this sort of thing. But then I wondered, like, what would it tell you? This is along the lines of Kevin's question, but would it be interesting to know the shape of some, this question I just asked? If we plug it into ChatGPT and get these numbers out, would that be interesting? Would the topological structure be interesting?
So I have not looked at LLMs in the context of this. Now, it is true that they have notions of distances between words, because they're actually based on what the people in that community would call embeddings. So there is some distance there, although I believe that the assumptions that they make, you're saying no. So I'm getting this.
I think that they go beyond that. I think the attention heads, you'd have to ask somebody who actually knows stuff, but the attention heads are designed to not just do the word embedding, but to look at the actual sentence and make better guesses. That, like, if I say David and Dan,
the thing is that when you're also using things like n-grams, if I do I do bag of words, do I do 2 consecutive words, do I do 3 consecutive words, you also get an explosion in computation time there. And at least the papers that I know, and this is not, ChatGPT per se, but rather just looking at more academic style, or let me say research papers, because they're not all from, they're academic style, but not necessarily from academia. A lot of those papers are still starting with bag of words. I mean, there's some that don't, but it still seems like a lot of them. I mean, again, I don't know what ChatGPT per se, how sophisticated they get, but I do feel like a lot of the papers are still using bag of words. And of course, bag of words is you start there, but we know the English language has to go beyond 1 grams, right? Like we know that. So I don't think I would, if I were going to do it that way, because I know that, that I would actually, maybe this is just me as an academic speaking, I would actually not start out doing that through ChatGPT, but would rather implement some method, whether it's a known one or whatever, that's kind of something that hopefully is underneath some of the ChatGPTs, just to know exactly what the method is, because this ChatGPT then still takes a black box type form, right? Since I don't know exactly.
Yeah, you don't know where but you're same with a city map, right? Like it is just data that supposedly has something to do with the sentence structure. But I think my main question, and maybe it's maybe not that interesting, but like what would it mean is more along the lines of like what would the topological Getty numbers tell you about if it really was perfect at saying which words were associated with which words?
I think my short answer is I don't know. There was one thing that I was using that had words that we had a project that we started, and hopefully get back to at some point, but we were basically getting results that we didn't understand, and that was to look at song lyrics. And the reason we were doing this is because we were thinking that the notions of having choruses should give you this periodic structure that maybe you could get holes related to that, but every attempt that we made just gave us stuff that we couldn't interpret. And we're interested in the project, but we basically are like, okay, we don't understand any of this in terms of output.
Gotcha.
And we were doing song lyrics partly from our own interest, but also partly because we felt it would have more structure than many other pieces of text.
Okay, well, thank you. I think there's one more question, by the way. Maybe I should open it up to the seminar room here at Topos.
Yeah, the seminar room has a hand up.
It does indeed.
Hi, thanks much. Can you talk a little bit about, coming from the application side, sort of how you explain when topology is what people should care about rather than distance?
Right. Well, I mean, the reason in this case, the reason was more we didn't want to make arbitrary choices, and time is actually definitely more relevant in distance in that one. So in this case, we were just sort of learning about the application ourselves and coming from human experience. This is one reason why I find social systems easier than biological systems, because human experience gives you some knowledge of social systems, and biological experience, you really do need the biologist. But in terms of when it's useful and when it's not, I think that this is something that we're still trying to get our head around, because a lot of what's going on is, oh, here's a fancy tool, right? Here's a flavor of the month. Let's try this tool on everything to see where it helps. Or I am trained in X, so therefore I'm going to use X because I have a hammer and everything looks like a nail. And so I think that figuring out when this will really be the best thing to use as opposed to other approaches, I think that's something that we're in the process of. One thing that I find nice and that I've thought about a bit is that because I've done a bunch of stuff with network analysis, that is often one of the alternatives. And so one of my goals sometimes is for myself to see what do I gain from network analysis versus what do I gain from this complementary approach. And there are various problems that a number of people have studied in multiple ways. And in fact, this has to do with how I got into TDA in the first place. So let me show you this picture. I showed it to you earlier on this granular materials picture. So one thing I did not say, this has been studied using TDA. So Konstantin Machaikov and his collaborators have done that and have done a bunch of things. And it also has been studied in network analysis, including by my collaborators and me. And systems, not just granular materials in general, but granular materials exactly of this type. Even from the same laboratory or from related laboratories. And so there are some examples that are out there, this being one of the prominent ones, where you see what the different approaches give you, and they give you complementary things. So I don't think it's going to be like you always should use method X on a certain problem, but rather it complements other things. where things go in the steady state of when it should exactly be used, I think we're not there yet. There's definitely a lot of dart throwing going on. So I don't think that's a perfect answer to your question, but I feel like that's kind of where things are.
Thanks.
Great, thank you. So why don't we end here and thank Mason again.
Yeah, thanks very much. All right, I'm gonna head off then.
Clapping in the room. Okay, thank you.
Yep, bye.
Bye.